Hey everyone and welcome to this bonus episode on third-person shooters. I was only planning to do 3 episodes, but when I was looking at my footage and editing the previous videos, I realized that I mentioned quite a few times about how it's different when you're on console or how it's more difficult when you're dealing with controllers. So I figured, hey, why not do a bonus episode exposing all the
quirks and features
of console players. So, if you haven't seen the previous episodes, I highly suggest you go and have a look because we're going to be building from this. But just in case, here's a quick recap of what's important. So we have a character with a kind of basic world. This character is a model we imported from Mixamo, and it has an animation player and an animation tree that will drive the animation player based on a bunch of different states. And to change between those states, we have a script. And in the physics process, we handle different inputs and we move the state machine based on these inputs. Now in the main scene we have the camera that also has a script, and this script is responsible for moving the camera around the player based on the mouse drag. Now what we want to add is support for something like this. This is one of the cheapest controller I could find, and I bought it at a really weird electronics store close to my house. And it actually kind of doesn't work by default with Windows because I discovered that this is a Wii U Pro controller. But luckily I found a little app that allows me to remap the input from the Wii Pro controller to standard Windows controls that Windows can understand and map properly. So I just need to connect it and load a profile and we're going to be good to go. Now, hopefully you have like an Xbox controller and you don't need to do that, but this is still really nice because it allows me to see the actual raw input that Windows gets from my controller, so I can see if there's any drift or anything, and I can see that all the keys are working. So it's really helpful to have something like this when you want to test. Now, since the left stick and right stick are basically going to be the same thing, I'm going to set up a script in my main scene just for handling the inputs from the joystick. So I'm going to just create a new empty node here that I'm going to call the left stick. And I'm going to add a new script in my script folder that I'm going to call thumbstick, because this is going to be generic for both the right stick and left stick. Now in the script, I want to get the values from the stick. And to do this, well, I have to go into my project settings in the input map and I have to add some mapping for these sticks. So if you remember, we already had a mapping for WASD to move our character around. So this part, we're just going to add an alternative input with the left analog stick. That's going to be left like up and left down and so on. Now for the camera, we actually use the mouse, so we don't really have any input map, but that's easy. We can just add new input mapping, like look up, look down, look left, and look right. And we're going to do the same thing, but we're going to add the right stick in this case. Now that we have that, we can read the values of our input stick. Now the thing is, I want this to be generic for both the left stick and right stick, so I need to be able to configure which input I want to get. So I'm actually going to do an export for the value of the action map. So we're going to call it var action up and do the same thing for all the position of our stick. Now you'll notice that Godot actually splits the positive and negative input of the stick into 2 separate variables, but that's fine. We can just combine them by adding them together again at the end. Now I'm putting the default value for the left thumbstick, but then when we are going to copy this for the right thumbstick, we can just change them in the editor. Now I'm going to be doing quite a bit of processing on the raw input from the thumbstick. For now, I'm just going to try to pass them as is, but because of the processing I'm going to be doing, And if I'm getting the value multiple time every frame, I don't want to do this processing multiple time every frame. I want to make sure I do it only once per frame. So I'm going to be doing my calculation in the process method, but I'm going to be caching the result. So I'm going to add a variable that I'm going to call value. And that's going to be a vector2 with the value of my input. And because I want to be able to do some debugging, I'm going to also keep the raw value of my input. Now we can add the process method, and in the process methods, to get the value from Godot, we just need to call the input get action strength method with the parameter we just set up. And like I said, we can combine the two up and down or left and right together by just adding them together like this. And of course, we do it for the Y and the X. Now, in theory, that should already be enough to test a little bit to see if things are working, because since we've mapped the left thumbstick to the input for the player, we should already be able to make the player walk around by just using the thumbsticks. Of course, the camera is not working yet because we haven't implemented these actions. So let's do this now. So first, let's go into our character, and there we're going to need the information from the left stick. So I'm going to add a new nodepath export so we can link our thumbstick script to our character. And I'm going to call this the thumbstick, and I'm just going to do something like this. Now that we have the thumbstick, well, actually, we have to set it like this. Now that we have the thumbstick, we can go into the physics process method, and where we used to get every keys for the movement and change the value of the direction vector, we can now directly set our direction by getting the value we calculated in our script. And we don't need this anymore. Now, before testing, one thing I want to do is actually I have a debug visual that I created. Technically, you'd just be fine with printing out the values if you really need to debug. This is a little bit more fancy than what you really need if you're working on your game. But for the video, I thought it would be better if you can see what's actually happening to the thumbstick. And I can link them to my script so that we can just debug and see visually the input like so. And if you notice now, what is nice is that I can kind of walk opposite of the direction my stick is pointing. To fix this, what I'm going to do is just simply change the sign of the value so that it matches all the other stuff. It depends how you program your controls, but if you follow the tutorial, then you're gonna have to flip the input. But now you can see we can walk left, we can walk right, or vice versa. We can walk forward and backward, but what is nice now is that it's analog, so we can walk full front or slightly to the right, or a lot to the right. Now, to do the camera, we're going to do something similar. We can just copy our left stick and rename it to right stick. And we can go into the camera script. But where in the camera script, we were doing our input handling of the mouse in the unhandled input, here we're going to handle the stick in the process method. But it's going to be exactly the same thing as those three lines here. Also, just like in the player, we're going to have a link to our thumbstick script. So we're going to add this export variable, and we're also going to call it thumbstick. And we can set it by just clicking on the camera, assigning the right thumbstick. And also, not to forget, the right thumbstick, we need to change the names to the mapping we added before. So that's going to be look up, look down, look left, and look right. And with this, we can go into our process method, and what we're going to do is get the value from the thumbstick, just like we did for the player. And if the thumbstick is actually pressed, because I don't want to do anything if the thumbstick is nearly 0, then we're going to do exactly the same thing we were doing in the unhandled input. So we're going to set the rotation of our camera and clamp it to the max pitch limits that we set before. Now, yeah, that's copy and paste, but it's just 3 lines, so I think it's fine. And now, if we run the game, we should be able to turn the camera with the right thumbstick. Yeah, okay, that might be a little bit too fast. Now, I prefer to have my thumbstick script be as generic as possible, and so I'm going to make sure that the value that we return is normalized between -1 and 1. But of course, this is too much for the camera rotation, so we need to multiply it by some kind of factor. Now we can just do something like this, multiplying it by, say, 10%, and it should already be a lot better to look around. Now again, the camera is not turning the right way. For some reason, my X are flipped, but that's fine. We're just going to change the sign here. And now it's working pretty well. The first thing we're going to want to correct is that, like I mentioned in the previous episode, when we're turning in yaw, we have 360 degrees of freedom, but up and down, we've limited the pitch, so there's only about 125 degrees of freedom. And since the stick is actually always between -1 and 1, it feels like it's much faster up and down than left and right. It's actually the same speed, it's just that there's much more degrees of freedom left and right. So what we are going to do to make it feel much better is we're actually going to reduce the speed of rotation for up and down. And already it feels much more proportional. It means it feels much more natural. Besides, you rarely want to look up and down really quickly. Usually when you're looking up and down is because you need some kind of precision. So you'd rather have it be a little bit less sensitive than when you want to look left or right. Now the next thing we want to do is, if you notice, no matter how much I push my controller, we're always walking at the same speed. Like as soon as I trigger the move, it's going to be walking like a normal speed. It would be really nice if we could control also the speed the character is walking. To do this, we have to go back into our character and we have to go play a little bit in the animation tree. What we're going to do, I'm going to do it only for the walking, but if you wanted to do it for the running or the jumps or something, then it would be basically the same thing. I'm going to replace the walking animation with a new blend tree. And this blend tree is going to contain the animation that we had before, the walking loop, but we're going to add a time scale in between. What that's going to do, it's going to allow us to control the time scale with the length of our input. Basically, the magnitude of our thumbstick is going to decide the time scale of the walk animation. So if we go back into the root of our state machine, we can get rid of the basic walking animation and we're going to rename our blend tree walking, and we have to redo the transition like so, and we have to set them up with a little bit of fade time like we did before, just so that everything looks smooth. Now, if you look in the properties of the animation tree, we're going to have here in the parameters, we're going to have walking, time scale, scale, and if you hover over it, you can get the name of the parameter we need to set in the script to control the speed of the animation. So right here, where we switch to walking or running, I'm going to do anim3 parameters, walking, time scale, scale, and we're going to set it to the length of our direction vector. And since I said I want to normalize the length to -1 and 1, then the length is always going to be something you can multiply the animation and get a different speed. And if we test this, you're going to see that if I move just a little bit, the character is going to be moving really walking really slowly. And if I push all the way, then he's going to be walking fast. So this might be a little bit too simplistic. Really, you probably want to do some 2D or 1D blending between different animations for walking and running based on the length of the input you're giving the controller. But I'm not an animator, so this is a little bit out of my comfort zone. So I just wanted to show you a quick way of doing a bit of this. But if you really want to make it beautiful, you're going to have to spend more time understanding the nodes and how to build your animations and all that so that it all blends well. But for now, I think that the basic concept is going to be like this. Now, if we go and bring back my little Wii U Pro app, and you have a look at the input, you're going to notice something a little bit strange. See, my input here in the Wii Pro says it's 0.3, but Godot says it's just 0. Actually, I have to go all the way to 0.5 to start seeing an input here in Godot. But even then, my controller says it's minus 0.5 and Godot says it's minus 0.03. What the hell? Of course, if you're familiar with Deadzone, you're going to have noticed that in the project setting when we set up our gamepads, there's something called the Deadzone here, and by default it's set to 0.5. That means that Godot will completely ignore half of your joystick input. Now this is something really important because nearly every player has really old, shitty controllers that will have some sort of drift. And what drift is that when you're not touching the controller, there's actually still a little bit of input. It's never completely zero. I'm actually really lucky that this completely shitty controller actually doesn't have any drift yet. But one day it's gonna have. So I'm gonna need a Deadzone if I don't want my character to always be moving slightly to the left or to the right because the controller is drifting. That said, 0.5 might be a little bit too much, and also I want to be able to have much more control over it. So I'm going to set them to 0 here in the configuration, and I'm going to be handling them myself in my thumbstick script. If we go back into our script, we're going to start implementing the Deadzone. And actually, I'm going to implement a double Deadzone. So I'm going to expose a variable to set it up from the editor, and I'm going to call it the Deadzone. And it's going to be a vector2 because I'm going to have an inner Deadzone and an outer Deadzone. You see, I've seen some controllers that not only had a little bit of drift, but also couldn't reach quite 100% input. And when that happened, it could be that your character is not able to run at full speed because it doesn't have 100% input. So you can have an outer Deadzone that will say that, for example, when the input is 0.9, well, consider it to be like 1. Let me show you a little bit what I mean. I have a graph here. You see, this is the input at the bottom of your controller. And as you can see, at 0.3, for example, see, I've set up my Deadzone here. At 0.3 and before, the input is going to be considered 0. So that if you have a little bit of drift around here, then it's not going to move your character. Though you don't want to start the input at 0.3 when the controller passes 0.3. You want still the player to have the full range of control. So you have to remap the 0.3 to 0, and then you have the outer Deadzone. So you want your input to be maxed when the actual input is a little bit below 1. So that's what you have here. I'm basically remapping the whole range of real input inside this inner and outer Deadzone. If you're familiar with your algebra, you know that this is just a simple line and that the equation for a line is ax plus b equal y. So in our case, x is the real input and y is the input we want to remap to. If we know the inner Deadzone and the outer Deadzone, then we can calculate the a and the b in the formula I just said. Now I'm going to leave you to figure out what you need to do to calculate these values, or you can just look at my code and copy it. I don't mind. Now you'll notice that this is between 0 and 1, but our controller goes to -1 to +1. Honestly, I have no idea if it's possible to handle this with the sign included in the whole thing. I just can't figure it out. My sanity is not good enough to figure it out. So my solution for this is just to use the absolute value while I'm doing my linear interpolation. And then after that, I just reapply the sign to the result so that I remember if it was minus or plus. But while I'm working with my numbers, I just work with positive number. I just find it way more easy. So what I'm going to do is have a variable that I'm going to call the Deadzone output. And I'm going to get the absolute value of my values right now. And I'm going to be working with this to calculate the linear interpolation of my input. Now the first thing I want to do is clamp the values within my inner dead zone and my outer dead zone. To do this, I'm just going to do a deadzone output.x equal clamp deadzone output.x deadzone.x deadzone.y. Now remember that x and the y in the dead zone is actually the inner and outer. It doesn't have anything to do with the axis. And I just need to do the same thing for the y. Here you go. And now to calculate the linear interpolation, there might be some tools to do it in Godot, but it's not that complicated, so I'm just going to write the formula myself. Now one of the things is that if the input is 0, the assign method from Godot is actually going to return 0. It's going to mess up with my calculation, so I'm just going to skip it, because if the input is 0 anyway, I don't want to modify the raw value. And to do this, I just do the formula for my linear interpolation. And at the end, I multiply by the sign to get back the sign I remove with the absolute from before. And I do exactly the same thing for the y. And now we can set our dead zone to be, say, my 0.3 and 0.9 for the outer dead zone. And the inner dead zone. We set it for both the left stick and right stick. And if we test now, as you can see, I've made a little debug display to show the inner dead zone, and the green cursor is the actual output, and the red cursor is the value I read from the controller. And if you see, the value I read from the controller is moving, but the actual input stays 0. But as soon as I pass the dead zone, then the green cursor starts moving, and by the time we reach the maximum input, then the green cursor also match with the red cursor. And that's how we program the dead zone. The nice thing here is that it's going to be really easy for you to expose it to the player so that he can set his own dead zone. I haven't made a circle for the outer dead zone, but as you can see, when the input is 0.9, the output is actually 1, because we're maxing at 0.9 and not at 1. One thing you might have noticed, if we're walking left and right, that's about the speed our character is walking, and that's about the speed of the animation of our character. But when I start walking in diagonal, for some reason, it looks like he's speeding up. Right? Diagonal. Right? Diagonal. Now why is that? Well, you might think that your joystick is a circle, but no, it's actually a square. Because when you're in diagonal, your values are 1, 1. And when you're left, the value is 1. And the length of a vector 1, 1 is actually 1.444. So the square root of 2. So that means that where we did our scaling in the character before, here, based on the length of our vector, it means we're scaling by 144. Which means we're actually making the animation nearly 1.5 times faster when you're walking in diagonal. You probably don't want that. Luckily, there's a formula to remap the square input to a circle. Now, I'm not good enough at math to really understand how that works, but I'm good enough to copy a formula from the internet. So what we're going to do is remap input to circle. And here's the formula to do it. First, I have to remember the original values. Then I can set the value of x to be the origin x times square root of 1 minus origin of y times origin of y divided by 2. Now, I don't really understand the formula, but I've tested it and I know it works. You can Google remapping square to circle and you're gonna get beautiful pages explaining to you the math behind it. But honestly, for me, it doesn't matter. All I want is for it to work. And that's what I'm gonna do. Now, it's pretty simple, but if I run the game again, as you can see, my raw input in red is still going from -1 to +1, but the green remapped input stays perfectly inside the circle of our input. And that means that when we're walking in diagonal now, the character is moving at exactly the same speed as when we're walking left or right. Perfect. Now you might think that this is done. We've got everything and it's working perfectly fine. The problem is we have to think about how players play games, and we have to try to make their life easier so that they're not going to be really angry at the controllers. And to do this, we have to understand how players play games. Usually, a player is going to be either going at full power or he's going to want to have a lot of precision. Now, the problem is if you let the player rotate the camera around really fast, then even an input of 0.01 is going to be too fast for the player to really do something precise. The solution to this is, again, to remap the controls so that an input of even 0.5 is going to be a really small precision number. Now, let me show you what I mean with another little graph. See, again, let's say that at the bottom, it's the actual input from the controller, and on the left is the value we want to send to the game. We want to say that, for example, if the player is doing an input between 0 and 0.5, then actually we want to give him a lot of precision and we're going to return values between 0 and 0.1. Then, if he's in the middle range, we're going to ramp up a little bit, but still give him some precision. Now, at 0.8 input and between 0.8 and 0.9, for example, we kind of assume that he's probably anyway going all out, so we're going to just quickly ramp up to the full input because probably he's not trying to do something precise in this range. So as you can see, we have various areas of input here. Now, it might look like an exponential curve or something like that, but in my experience, you want something very controllable because an exponential curve is still going to feel a little bit wrong. You really want to be able to control each of your zones. This is something that works kind of well for me, but depending on your game, the speed of your animation and all that, these zones might be completely different. You might have even more than 3 zones. You could have 4 or 5 or something like that. Now to implement this, we're going to go back again in our thumbstick and we're going to add a new export variable that we can configure. This time it's going to be an array of vector2. And we're going to call that the remap. Now, one thing that's really important for the remap is that we want the remap to start at 0 and to end at 1. Just so that the math can stay simple. And like I said, I want to have several zones. So the first value of our vector2 is going to be the real input. So in this case, up to 0.5, I want to remap the input to 0.1. And from 0.5 to say 0.8, I want to map the input to 0.5, for example. And then at 1 input, I want to map the input to 1. Or maybe this should be like a 0.6 or something. Now again, the math for this is a little bit complex, so I'm going to make a method for that. I'm going to call this the remap, and I'm going to do this. Since we already normalized the length of our vector to a circle, we have to consider that we can't just take into account the x and the y individually, because now when you're in a diagonal, the x maximum value is 0.7, because otherwise we would have a vector length of more than 1. So we have to do the remapping on the length of the vector and not on each of individual direction. But that's very easy. We can just take the direction vector, take the value normalized, and then I'm going to get the remapped length based on the length of the current vector, and then I can set the value to direction times L. And I'm going to make my method do remap. It's going to take a value of a float, and it's going to return a new float, remap to what we wanted. Now the math here is a little bit complex. Again, I'm going to use the absolute value because I just don't want to deal with the minus sign. And again, because Godot returns 0 for sign if the value is 0, I'm going to just escape so that it doesn't mess up my calculation. I'm just trying to find the mapping that comes before and after my current value. And once I have that, I'll be able to linearly interpolate between those two values, just like I did for the dead zone thing. So this is in the case that my value is actually inside the first mapping. Otherwise, I'm going to iterate in my map to try to find where my value is inside my mapping. And that's why I said it's important to map all the values between 0 and 1. Otherwise, this code needs to get a lot more complicated. So if our value is between our two mappings, then we've found where we need to interpolate, and we can use these two mapping to do our linear interpolation pretty much in the same way we did the dead zone interpolation. In this case, I'm using the lerp method from Godot, but it's basically the same thing. And we return the result times the sign, of course, of our original value. So we get back the minus sign. And now with this, and if I do the same thing for the look around, if we run the game, you're going to see that now if I have an input of say 0.4, then you can see that the output is actually 0.6. But again, once we reach 1, the whole input is going to be in. Now, of course, it's getting a little bit difficult to see because with all the different things we've added, it's a little bit hard to figure out what's happening. For example, like there's the dead zone, and actually our remap is after the dead zone, and then there's the remapping to the circle, and the remap of our different areas of precisions are after the remapping to a circle and all that. And you can play around with these, and you're going to have to tweak them a lot, and it's going to depend on your game. But as you can see, I can rotate around the character really quickly, but now it's much easier to do very, very small precision movement because I have a whole half joystick to do between 0 and 0.1. Now I figured this out by actually looking at Assassin's Creed Unity, who does the same thing. I used my little Wii U Pro control here, and I checked when I have an input of 1, how long it takes to circle around the character in Assassin's Creed Unity. And I got something like a 0.5 input would take me about 18 seconds to turn around the character, which is really, really slow. But already at 0.7 input, it would take me 9.5 seconds. And at 0.9 input, which is nearly maximum input, it would still take 7 seconds. But then when the input is maxed at 1, it takes only 3 seconds, which is nearly 2 times faster than at 0.9. Now, one last thing I like to add is something I call the acceleration. But actually, it's a limit on the acceleration. You see, besides giving the player a bigger range of precise movement, a lot of players will tend to tap their controller when they want to do very small movement. And we can help them by limiting the speed at which the player can go from 0 input to full input. Now, this needs to be really, really small. You don't want the player to feel like the controls are sluggish, but if it takes, say, 3 frames to go from 0 to full input, the player is not going to notice, but when he taps the controller for just 1 frame, then the input is going to be, say, 0.5 instead of being the full 1, which is going to give him a little bit more precision. Now, to do this, we have to go back into our thumbstick script, and we are going to add another variable, and we're going to call it the max acceleration. Now, this is basically how many seconds it takes to reach full input. So when I put it at 5, it's actually 1/5, which means it's going to take like 1/4 of a second to get to full input. Now, because this is going to be based on the input from the previous frame, we also need to remember the value of the last frame. So I'm going to add a new variable that I'm going to call previous accel. Now, this one is a little bit special because I want this acceleration to be applied after the dead zone, because I don't want to accelerate inside the dead zone, but I want it to be applied before the other things we did. So I'm going to apply this before the remap input to circle, but after the dead zone. And I'm going to call this the accel. And basically, I calculate a max change rate based on the delta from the update. And I have a really complex condition here, because you see, it's fine to have an acceleration when the player taps, but when he releases the control, you don't want to have some drifting where the character is going to keep moving because it takes 3 frames for the control to go back to 0. So if the input is going in the opposite direction of the previous frame, we want to snap to the value. We only want the acceleration when the character is moving the thumbstick in the same direction as the previous frame. And that's what this condition is going to do. It took me kind of a while to figure out how to calculate it. And so I'm not going to explain all the values here, but let's just say that this condition is basically doing what I just said. It's only applying the change when the movement of the thumbstick is in the same direction as the previous frame. And in that case, we're going to limit the movement of the thumbstick based on our max change rate. And again, we have to play around with the absolute value because I don't want to mess with the plus and minus sign. And we have to do the same thing for the Y. So I'm just going to use the Y here everywhere. Hopefully I don't forget one. Yay for copy and paste. And of course we have to remember our previous acceleration. And now, if we test, if I maximize the window, we should see that the green cursor is lagging a little bit behind when we first start to move, but you'll notice also that it snaps back just as quickly as the red cursor when we're going in the opposite direction. And this allows us to do very precise movement. For example, with the camera, if we're just tapping, you can see the movement is very, very precise because the character is tapping and we're just letting him go to, say, 0.4 or something like that. And with this, you have a pretty complete and really flexible control scheme for your console controllers that will let your player feel like the game is like a AAA console game. And this is basically all the passive settings you can have for a console controller. I say passive because after that, there's also active cheats that you can do to help console players. I'm sure you've heard of words like friction, magnetism, or auto-aim. These are all active methods of helping the player aim where you think he wants to aim. Now, the problem with those methods is that not only they're much harder to implement, but where the passive method, a really skilled player will eventually get used to them and he'll be able to get the same results every time, these active methods really depend on the environment you're in and can have really bad side effects if you don't carefully implement them. For example, let's say you tend to drag the bullets towards the body of a character to help the player aim. Well, a player aiming for the head might miss the head because we're helping the bullet go to the body of the character instead of the head, which is going to frustrate player incredibly a lot. Now, sadly, this video has been going on for way too long for me to get into all of these active helper or cheats. So I'm going to leave it at this because I think it's already a pretty good base. But if you're interested in like these things like friction, magnetism, and auto-aim, then I'll leave a link to a paper explaining a little bit the methods, and maybe I'll make another video at some point on how to implement these inside Godot. But like I said, these are much more difficult to get right, and they're going to be very dependent on how your game is implemented and what your game is. And with these wise words, that's it for this week. I hope you liked it. I hope you learned something. And if you did, please subscribe, leave a like. It helps the YouTube algorithm. And see you all in my next episode. Bye!